But now we want to do more complicated things. For example, we want to discuss bulk materials, either bulk 2D or 3D materials, and we want to develop the sort of technology that's required to describe them. This is, of all the things that you've done so far, a little more mathematical than earlier things, mainly because the natural language for thinking about continuous media are vectors and tensors. Tensors can be thought of as a generalization of a vector. A vector is a quantity where at every point where I have some direction. And a tensor is a somewhat more complicated object. A vector in 3 dimensions has 3 numbers associated with it. A tensor has 9 numbers associated with it. In some contexts, it may be easier to think about them as types of matrices, which you can write down, which behave in a specific way when you change your coordinate system. Alright, so what are examples of these in a biological context? One example, of course, is when you look at the cell membrane here. So suppose we are looking at red blood cells. So the red blood cell membrane is a lipid membrane. So it has these little molecules that we wrote down with heads and tails, and it's a bilayer membrane. So that's essentially 2 sets of these molecules here. This is a very thin layer here compared to the typical size of the red blood cell, which could be of order microns, several microns. But in the real red blood cell, under this, there's also a polymeric layer, which is made up of a molecule called spectrin. And these spectrin, this network of spectrin molecules underneath, is tied to the bilayer through another molecule called ankyrin. Okay. So this network here can either be 4 coordinated or 6 coordinated. It looks like this. If you sort of pull it out and stretch it out, this is what that network will look like. When I have structures like this, I need to ask what is the energy required to deform them or push them or change their shape and so on. And the reason this question is interesting is, suppose you have, for example, a network that branches like this, through which you need to transport a red blood cell. So remember that the red blood cell has a characteristic shape which looks a little like that. It's a biconcave disc. And as you go through the systems of veins and arteries inside your body, these begin to constrict. So the capillaries through which the blood passes can be very small. That means you have to worry about how much this is distorted or how much its shape changes as it's driven by the blood flow into these ever smaller constrictions that are the endpoints, the capillaries. If you want to ask that question, how much energy does it at some point stop because you don't have the amount of energy to drive it through or to deform it sufficiently to push it through? That's a question about what is the elasticity of an ensemble like this. How much energy does it take? So that's why we need to ask questions about how much energy does it take to deform a network of this form. That's why we'll use these results. The other example is the nuclear lamina. And this is a cell, this is a nucleus. And the nuclear lamina is sort of structure that sits just below the membrane here. And the membrane of the nucleus is a sort of interesting membrane. It's a double membrane, so it sort of looks like this. It's actually more complicated than that, but let's just draw it like this for the time being. Okay, so there's an outer membrane, inner membrane. These are pores or nuclear pores through which material is shuttled in and out. And below this, there is again a network of intermediate filaments called the lamins. Okay, and the structure here on the inside is called the nuclear lamina. Again, the nuclear lamina is made up of lamin proteins, and they have a network-like structure, which can actually be fairly ordered. In some electron micrographs, it looks like a square lattice. So given a structure like this, what we'd like to ask is, what's the energy that is required to distort it, to pull it, to stretch it, etc.? Because that will be a very important part of how we describe the physics, the structural aspects of the biophysics of structures like this. Okay? All right. So if you remember what we did the last time, we were looking at structures and looking at ways to deform structures. For example, little cubical blocks that I might cut out of a larger system. There, a priori, there seem to be two distinct things that you can do to this. One is to deform it, for example, apply a uniform isotropic pressure to this. It's sometimes called a hydrostatic pressure that pushes in from the outside to the inside in all directions. Okay? As a consequence of this pressure, this system will distort a little bit and maybe become this much smaller cube. So we need to ask what is the energy required to perform this distortion. And this distortion is a volume changing distortion. Okay. So this is a volume changing distortion, but you can have other distortion which consists of taking your initial cube like this and distorting it like this so that each of these faces becomes a parallelogram. These are distortions that leave the volume the same, so the volume doesn't change, but the shape changes. Okay? If the volume doesn't change, that means you have the same number of particles, slightly distorted from the initial position, confined to the same volume. Okay? All you're doing is changing the shape of this particular structure. So potentially the energy cost for this is a different number or discounted differently from the energy cost for this. So one way of writing the energy cost for this, just to say that the energy required to create this deformation is proportional to, or the force required is proportional to the change of volume, delta V, divided by V. And write this down. So the pressure required to create this is equal to some elastic constant there, and I will use the notation K with a minus sign. So this is the fractional volume change So if the initial volume of this block was V, the final volume is V minus delta V, the change in volume is delta V, the fractional change in volume is delta V divided by V. So this quantity is now dimensionless on this side. So the pressure that is required, the uniform hydrostatic pressure acting from all directions, that's required to change the volume by an amount delta V, is related to a quantity called the bulk modulus in this particular way, where the pressure is the bulk modulus, but the minus sign is because it pushes inwards, so delta V is negative. Therefore, I need a minus sign in order to compensate that negative to keep my pressure positive. Okay, that's just a choice of how I define my pressure as acting positive if it acts inwards to compress a particular structure. So here is how I would describe volume changing deformations in terms of the pressure required in order to push these things to make V minus delta V. The pressure is the force per unit area. So in that sense, it's like the old strain, the old stress term that we wrote down. Okay. Okay, so remember this other picture that we drew where we had a picture like this, and this could of course extend further, we weren't worried about that, and we said let us deform this by a certain amount so that it looks like this. So these were, as I said, shear deformations which keep the volume fixed so that delta V equal to 0, but nevertheless change the shape. We know that because if I just take this parallelogram and make it like this, the area of this is just the base times this height, but the height remains the same as I deform it. So how do I quantify this deformation? I have deformed it like this. So the picture is that suppose I just look at the two-dimensional version of this. I have a force that acts on the top. That force pulls all molecules here by a certain amount. Every molecule on the top. And the bottom part is anchored. So that's one way is to push molecules at the top and anchor the bottom. The other way is to push all molecules here in this direction and exert an equal and opposite force on the backward direction. So that will keep the central point the same, but things will be distorted around that. This is called a shear deformation. Okay. And as I said, these deformations don't change the volume, and we want to find a way of finding the energy cost of these. And if you remember what we did the last time, we said let this move by some distance d, let this height be h, then the analog of the delta v by v is d divided by h. It vanishes if there is no distortion at all, and if the larger the h is, the more smoothly this is spread out from beginning to end. So if it's very, very large, if I take a very large system and change it by a very small amount compared to this h, the energy cost required to do that is relatively small, because I'm not distorting the system very much, which is one reason why you want to have this dimensionless quantity here. And over here on the left hand side, we wrote sigma, which is the force per unit area, so the force acting on the molecules in the top layer to deform them. And we said the force per unit area was proportional to, in this particular case, we said G times, we call this quantity gamma. Okay? So the gamma was the strain, and the relationship sigma equal to G times gamma, I said, is really the same as Hooke's law. It's just one particular way of writing Hooke's law, which says force and displacement are proportional to each other. So the force per unit area sigma required to create a strain gamma is given by G times gamma, in this very simple way of drawing it. Of course, in the more complicated case, sigma and gamma have more indices. Gamma is just a deformation in the x direction as you move in the y direction. So one way of saying it is that every point here is displaced by an amount u, which is just linear, so this is just gamma times the distance in the y direction, and u is in the x direction. Okay? So what this means is the following, that here is my distorted system here. A point that was initially here has moved here, a point that was initially here has moved here, a point that was initially here has moved here. Okay? So depending upon where you are in the y, this is x and this is y, everything, the displacement points in the x direction, so there's an x hat here, but the amount of the displacement, how far each point is moving, depends upon where it is along the y axis. So for y equal to 0, it hardly moves. For y equal to h, this is d times h divided by h cancels. So this is moved forward by the distance d, exactly by construction. Okay? So now you can see that I have the u, the x component of the displacement field u is in the y direction. So I have, in general, I have to worry about quantities like the derivative of u in the y direction, the derivative of u in the x direction, and so on and so forth, in a more general way of thinking about this problem. Okay? So this is an equation that is appropriate to solids. The G is called a shear modulus. Sigma is called the stress. Gamma is called strain. And this is the simplest way of thinking about what happens when you try to deform a material that is solid-like. So if I actually were to draw the sigma here and the gamma here, what I would get for an ideal solid would be an ideal Hookean solid, let us say. Is something that is linear, if I put sigma with gamma, and the slope of this is the elastic constant, the shear modulus G. Okay? The second thing is, if we are not talking about, so what is this saying? This is saying as long as I impose a fixed strain, I have to provide a certain amount of force to maintain it at that position. Okay? And then we spent some time the last time arguing that this is not true for a liquid, and asking what is the distinction between a solid and a liquid. And we said liquids can flow, solids cannot flow. So again, this is, as I said, there's a mathematical part to this, but there's also an understanding and a sort of physical intuition part of it, which is why all of this discussion is actually quite important, because in many cases you will talk about viscoelasticity of gel networks inside the cell and cytoplasm and so on and so forth, which are more complicated properties that interpolate between both the solid and the liquid. So when we want to talk now about liquids, the simplest way of thinking about a liquid is that the stress here, the y-axis, the sigma, does not depend upon gamma, but on the rate at which gamma changes, which is gamma dot. Okay. So if I just take a liquid in a box that precisely contains it and change the shape of the box from here to here without changing its volume, there is no restoring force. The liquid is perfectly happy to fit into any volume that I squish it into, any change of volume, provided I don't compress it. Compression always costs energy, whether I talk about a solid or a liquid. But a liquid is somewhat unconcerned about the change of shape, which is why we define a liquid, if you remember in school, as something that takes the volume of the container that you pour it in. So that's the analog of this. It doesn't sort of remember where it came from, what its earlier state was. Anything that you do to it is perfectly happy to go along with it, along with any change of shape that you actually maintain. So sigma versus gamma dot is again linear, and the slope is a quantity called the viscosity. So sigma is eta times gamma dot, and this is true for a liquid. Here the different terms are the viscosity, eta, the strain rate, gamma dot, and the shear stress, sigma. And these have the same units. The sigma is a force per unit area. Gamma is dimensionless. Gamma dot has the dimensions of 1 over time. Therefore, eta has a dimension of force per unit area into the time. This dimension of this is the dimension of the quantity eta. Okay? You may remember eta from earlier. If you remember going back all the way, when we said we were thinking about describing particles, and we asked what is the diffusion constant of a particle of, say, some characteristic size A, some characteristic linear dimension A that was spherical. And we actually calculated this. We said D is ABT times 6 pi times eta times A. In a limit where this was large enough, it was spherical, and it didn't move at a very large velocity. That was, I wasn't sampling the behavior of the fluid at very high frequencies. Okay? This is the same eta that enters here. It's the same resistance to being sheared in time that enters over here. So this is just to sort of correlate the different etas that you have seen and say that they're actually very much the same thing. Okay. So now let's just go back and redo the old calculation that we had, where we were thinking about some structure here, some point P that moved somewhere else under deformation, and we wanted to ask, how do we describe this deformation? So the way we describe it is, we say that P was at time t equal to 0 or t0 was at location r0 at time t0. Okay, or at the initial time, I can take time t0 to be 0, where I start. So I know where it started off with, and for reasons to sort of explain, I can just start with the case where that is the undeformed state. So I have a block, something like this. At t equal to 0, it is not deformed, and then I bend it. Okay. So if I know what point I started out with, which is the point here, in some coordinate system that I will draw, now this point has gone to some other point here. So if I know where every point has gone, these are called material points because they are points within the material and they all contain some mass densities, momentum, some velocities, etc., etc., etc. So by telling you where all the material points in a material have moved when I distort the material, I have told you a little bit about the deformation of that material. So what I need to provide you is a vector. I will put a hat on this because the notation I had a little hat. It's not a unit vector, it's a new location. So if I know what is r hat at time t, so let me just put r hat is a function of initial location, but at some later time t, this for me has all the information about where the material points have gone and therefore what the deformation has actually been like. Okay. So this is position of material point P which was at R0 at time t equal to 0. Okay. How fast is that point moving? Well, we can define a quantity V which is just delta of R with a hat on it of R0 comma t divided by delta t. Okay. So this is V at point R and t. So this is what the velocity with which a material point at R is moving at time t, given that that material point started at point R0, time t equal to 0. So now, whenever we talk about continuum mechanics, we are not allowed to talk about strictly perfect points. We talk about small little volumes centered around them, look at the mass inside that and actually write down an equation of motion for that mass. That's the whole spirit behind thinking about things in the continuum. So the equation of motion that I would write is delta V of R comma t by delta t is the acceleration. Multiply this by the mass, which is rho times the small volume that contains those points. What I should have on the right hand side is the force. This is just Newton's law, which I have on the right hand side. So I should put a vector sign here for F. And this is, of course, the law that all classical matter is supposed to obey. It just says that these material points will move when acted upon by some external force at that particular time. Then we spent a little bit of time talking about what are the forces that should actually enter here. And we said, take your little volume here. This is a little volume V, which is supposed to be small. There is all sorts of matter inside. This matter can be acted upon by bulk forces and by surface forces. Bulk forces act on everything. They like gravity. They act on every little molecule inside, deep inside this particular volume that I've considered. Surface forces act really very close to the surface that bounds this particular region that you're considering. Often if, for example, if there are molecules that are moving just outside the surface, they will exert a drag force on the molecules just below because they're exchanging momentum with them. Those are the sort of physical situations that you want to model by accounting for the difference between surface and bulk forces. Let's now ignore the bulk forces because there are many conditions where you can actually do that and just look at surface forces. So remember how we did that. We said we can calculate the alpha component of the force acting upon a little surface with a normal in the n direction by saying that this is just sigma alpha beta n beta times the little area of that surface. So this is how I represent a force that acts on my little volume. The surface force. I say the amount of the surface force must surely depend upon the area over which I am exerting it. So that's where the dA factor comes. It must depend upon the normal to that particular surface, because whether a force is pushing inwards or pushing sideways, so surely the effect of that force is different on the mass that I'm actually considering. So the quantity that ties the alpha component of the force to the beta component of the normal is this quantity sigma alpha beta, which is called the stress tensor. So look at the logic that we followed. We said we're going to try find a way of understanding little parts, how little chunks, material points of this system behave. We wrote down an equation of motion, which is just Newton's laws of equation. Force is mass times acceleration. Again, something that you remember from your school. Then we said, how do we write this force in a manner that is more useful to us? We said, let us divide this force into a bulk force and a surface force. Ignore the bulk force for the time being. Then it's just what is the net force at every point on the surface. But remember, we're in the continuum. So instead of saying there is a net force F here, we have to specify several things. We have to specify where is the surface. And the surface you specify by every point on the surface telling you where is the normal that points from inside to outside, what is the location of that point, and what is the infinitesimal area that controls that. So this little surface element is actually the area of the surface times the little n hat that points the outside. Once I tell you that, I have to tell you what are the components of the force with respect to this little surface element. There are components of the force that are perpendicular to that, and there are components of the force that are parallel to that. So this essentially disentangles all of those things. And because this is a vector here and this is a vector here, this quantity here must be a more complicated object called a tensor. In order now to get the full force, what I need to do is to integrate along the whole surface. So the total force acting upon this, which is the total force here, is just an integral over the surface, area of the surface, times the force here. This is the sigma alpha beta n beta. It's just the integral over the subject. So now, remember what we did. We went back and looked at Gauss's theorem for this, which converted surface integrals into volume integrals. And then we said, this is just delta sigma alpha beta by delta r beta integral dv, which is the volume integral that encloses this particular surface. Okay. So the rho times v there, I could also write on the left hand side as integral rho, the volume dv, delta of velocity v by delta t given r and t equal to the integral over the volume delta sigma alpha beta by delta r beta times dv. And here I should put in the v alpha here. Okay, because this is true for each of those components. So now we have everything that we actually need to write our equation of motion. We now know what the forces are on the right hand side. We have now written them in terms of gradients or derivatives with respect to r of the sigma alpha beta. Okay. Now there are some situations where essentially, almost all of biology, you don't have to worry about acceleration terms. Everything moves very, very slowly. So we can ignore this particular term here. We already ignored all the bulk forces. We didn't worry about that. So the only term to worry about is this, and this naturally has to be 0 because everything else is 0. So the condition is delta by delta r beta, sigma alpha beta must be equal to 0. And this is just the condition of force balance along each of the components, along each of the direction, alpha equal to x, alpha equal to y, alpha equal to z. Okay?
So that would be just like assuming that everything is moving in the same velocity, right?
It sort of it's ignoring changes in the velocity, but it's not really assuming that things are they're moving with the same velocity. It says that suppose I impose a force, the change in the velocity is relatively small, so I can ignore the acceleration term. Things all happen slowly. Which is why the only term that survives at long times is just the force balance term. So in every configuration, as I change it from here to here to here, forces balance. And I can ignore the acceleration component of this. The analog of this is like saying that if I pull, if I take a spring and I pull it out, and then I release it. So under normal circumstances, you would have expected that spring to oscillate. But I put that spring in some environment, which is say a liquid or an oil or something like that. Then instead of oscillating, maybe it will sort of be, the oscillation amplitude will come down. Let me just draw that. So suppose I look at the spring displacement x of t as a function of t. Maybe it sort of started out like that, and this is a completely undamped case. It would go on forever. If I put the plunger, so suppose here is my spring, here is my ball, and I put a lot of liquid inside it, then even though I start here, the condition that I get looks a bit like that. It basically goes to zero. The amplitude vanishes. As I go to longer time, it exponentially goes away. If I'm very, very overdamped, essentially I go all the way here, but I don't even see that oscillation. I just come down and then I stick there. So this is a very heavily overdamped limit. So all the change in the velocity is really only over this very small time and not for longer. So if I want to describe it at times that are longer than this initial change, then where all these things have already happened, then I can just say forces are balanced. I'm going to forget about the acceleration term. It's the acceleration term that gives me this oscillation here. If I didn't have that term, I would just sort of go smoothly to zero at that point. So that's essentially what this argument here means, or what it's supposed to imply. For what is called a constitutive relation. And the constitutive relation, sort of apart from an equation like this, is something that relates the stress at any time to the history to which I have subjected it. So we want to try and understand what that is. So let's define a quantity which is called E alpha beta. It functions, but it's a function of the time t as well as the initial time t0 when I started deforming it. And this quantity is just delta of r hat of r0 comma t with alpha with delta of r0 beta. So let me just tell you what that is. So this is a complicated thing with lots of indices. So let's just understand what it's doing. It says, so let's say I have 2 points here. And I distort it, I do something to this. So maybe this point has gone here, and this point may have gone here to some later points. What this is saying is, what is the distance between the final points as a function of where they started off. That's why this is a derivative with respect to initial to r0. Okay, and this is r alpha, which is the later position. So how does this position change if I change this location very slightly? That's the definition. You can imagine that if I took this sample here and I just moved it here bodily, I'm not pulling or pushing at it or not letting any internal things happen to it. So that energy shouldn't change. So what is happening is each of these points here has moved to another point, but the distances and displacements remain the same. So it's only when there are changes, when the material is being stretched and pulled and sheared and twisted, that there is a deformation, there's an actual deformation in this material. So this is something we need to be concerned about. We said there was a final point and an initial point, and we described everything in terms of where that final point was, from terms of the initial point. So in all of our work was in terms of this quantity r hat of t, comma vector r, comma t. And we remembered that this r came from r0 at t equal to 0. This is how we started out. But this is on its own, this will not tell you, this is just telling you about where one particular material point goes. Somewhere, if I knew where all the material points were going, then I know how this is being distorted or changed, or the configuration is changed. But there is one thing that I must remember, that if I take this here and I just move it from here to here, pick every atom out and move them by the same amount, I haven't done anything to this except move it. There's no energy cost to doing that. I know from Newton's laws that if I just set it into motion, it'll keep moving and nothing will stop it. So it's only when I have parts of the system that move differentially with respect to each other, only then do I have a deformation that costs energy. So this is a way of trying to quantify that. It says where are these final points going as a function of where they were initially. Okay?
This is only if few of the material points are moving and few are not.
If, or they could all be moving, but they could be moving in such a way that the relationships between them are different at a later point. I'm just saying that the case in which all of these move by the same amount is a boring case that cannot really be a deformation, because nothing is moving relative to anything else. And there'll be no energy cost for that. So I want to describe something. The only way I can have an energy cost is if 2 points initially here have now moved somewhere else. And if I know the whole history of where any 2 points close to each other went somewhere else, I can map out the deformation of the entire system. So that's why this complicated definition is actually there.
So what is the beta index?
The beta, in principle, this could depend where the alpha component of where this was at some later time could depend upon the beta index of the separation at an earlier point. So suppose these were initially separated along this direction, but now these are separated along this direction. Okay, so I'm not keeping this the same. So in general, how much it's separated along this direction depends upon how much it was separated at a later time, depends upon how much it was separated in earlier time along other directions. So this just keeps track of that complicated spatial relationship between these. I can also define a quantity called kappa, which again has indices alpha and beta, which is the derivative of the alpha component of the velocity at point r and t with respect to r of beta. So this says at any time t, this tells you how much the velocity is changing in space. Okay? The reason for these complicated indices is because the velocity can be a complicated function of the spatial index. For example, I could have velocities all in the x direction, but which varied in the y direction. So in order to describe that fully, I need to tell you about all the components, what all of these components are doing with respect to each other. Okay? This is called a velocity gradient tensor. And this quantity here encodes the history of the deformation. Till time t. Because I can stop it at anywhere in between, I have to specify a full function as a function of t, where all of these points actually went. So here is a little bit of algebra, which I can do essentially in one line, that says that delta V alpha by delta R beta can be written as delta V alpha by delta R 0 mu times delta R 0 mu divided by delta R beta. Okay? And this I can say because there's a one-to-one relationship between where it was starting to where it was ending up. Okay? So 0 mu is the muth component of the position at time t equal to 0. This is the beta moment of the position at the later time t. So it's just breaking this up into two parts. Okay. But I know what this is. This is just E dot of alpha and mu, and this term here is the inverse of mu and beta. So in order to do this, you need to go back to the definitions and figure out why I call this. So if this is delta r hat alpha by delta r 0 beta, the inverse of this is this delta r 0 beta by delta r alpha, which is why it has that particular form there. And this term is a velocity gradient, delta v alpha by delta r 0, so that is E dot. Okay? Go back and check this. So essentially what this is saying is that E dot is kappa times E. And I know this because I can just write this in a matrix form. What is here is kappa as a matrix. What is here is E dot as a matrix. And what is here is E inverse as a matrix. So I can say that this is just, I can multiply by these matrices by E on the right hand side. So kappa matrix times E matrix is E dot matrix into E inverse matrix into E. But this quantity gives me the identity matrix, because the inverse times the matrix is just 1. Therefore, E dot is kappa times E. Okay. So given kappa, I can solve, given kappa and E, I can tell you exactly what is the sequence that this is going to be deformed by. Because then E dot, I can tell you what E is at a later time because I know what E dot is. So I can always take these quantities and figure out the whole history of the deformation. If I give you E at all times, you can calculate from that E dot, divide by E to find out what is kappa. Okay? If I give you kappa and E, I can figure out what is E at any later time. I give you kappa at one time and E at that time. I know how to make E dot. E dot tells me what is E at the next step. And then I can calculate from there, go back to kappa, etc., 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 and just keep going on from there. So these relations that are history of deformation, that how you connect the deformation to other measured physical quantities, are called constitutive relations. I'm just writing it down. It's a little formal, but it might be of some use later. So we'll just write it down for what it's worth. So let's do a few calculations that are simple enough to actually demonstrate on the board. we are going to look at a situation where R0 is here, and at some later point, R is very close by. So I'm not taking the system and just stretching it like this. I'm making a small deformation. So every point goes very close to where it was earlier, but is nevertheless deformed a little bit. So define the vector u as R minus R0. So this u at every point represents the deformation in the system. Either all the deformation, or you can also call it the displacement of all the particles in the system. Okay. Define a quantity epsilon alpha beta as the gradient of this displacement. So that is delta of u alpha by delta of r beta. Okay. So this is our old friend, the strain, because that tells me how much things are moving as a function of where they are. So now, remember that if I tell you at every point how much I have deformed it, I'm creating a certain stress in the system at every point, and I know if I assume that the relationship between stress and strain is linear, as I did earlier, then the stress sigma alpha beta must equal the strain epsilon not alpha beta, let me call this mu nu. But here there must be a more complicated quantity that connects these indices together, and this has lots of indices. This must have at least 4 indices, because it must be alpha, beta, mu, and nu. So it's C alpha, beta, mu, nu. The great rule of indices is that you can just sum up indices that are repeated. So mu goes away because mu appears twice, nu goes away because nu appears twice. The only indices left are alpha and beta, which must match the alpha and beta here. Okay? So this is the most complicated. Remember, this is exactly the same as sigma equal to g times, I don't know what I called it, eta, not eta, g times, what did I call it? G times gamma, gamma for the elastic case. That's really the same thing here. It's just a stress is strain, and the matrix here is the quantity here is a tensor called the elastic constants. Okay. So we've just taken that earlier definition and written it out in its full glory. The earlier deformation that we discussed is a very specific deformation, a very specific choice of epsilon mu nu, where I just sheared the system. And then there was just one number in the way I described it that multiplied that. So I needed to have only worried about the shear stress and the shear strain, and the number that connected the shear stress and the shear strain. But in general, if I pull it like this, it will experience forces in other directions as well. That's what all of these elastic constants try and account for. Mu and nu. Because if I said sigma alpha beta was just some number times epsilon alpha beta, that's making a very specific choice. It's just saying there's a number that connects them. If I have any two tensors, let me say some tensor sigma here and some tensor epsilon here, the relationship between, suppose sigma is required to have indices alpha and beta. So this must be, let us say that this is gamma and nu, and there must be some sum over all of these gammas and nus that correspond to giving an alpha and beta here. So one way of saying it, there is some quantity here that depends on the alpha and the beta, which is what appears on the left, as well as the gamma and the nu, which appear on the right. Because I sum over the gamma and the nu, I don't see them anymore. I only see the alpha and the beta. So this this requirement is because this is the tensor and because this is the tensor, the quantity that connects them must also be a tensor. However, it's a more complicated tensor than the earlier one that we studied. Now is the tensor with 4 components. And this is the most general way of writing the strain, stress, strain, the linear relationship between stress and strain for a material that is solid. And anything else that we do must be some approximation on top of this.
So the different modulars that we have are actually special cases of
They're all special cases of this. In fact, I wanted to try and see if we could actually do one of these together. And
How much elastic constants are there in the sea?
in principle, lots and lots, because the gamma and the nu, each of these are 3. So this is 3 into 3. Okay? Each alpha and beta, each of the alpha, beta, gamma, nu, etc. go over x, y, and z. So therefore, the number that this technically contains is 3 into 3 into 3 into 3, which is 81. So there are in principle 81 numbers that you must prescribe in the most general case. But materials are not the most general case. Often they have special symmetries. And those symmetries are often enough to reduce them to 2 at least, sometimes 3 or 4 or 5, but not much more, certainly not 81. In the simplest cases that we will consider, in this case, which is the case of isotropic materials, I only have to worry about 2 elastic constants. One represents the old bulk modulus, and one represents the old shear modulus. So that's what we'll try and do now. I'll actually show you where that comes from. So let's just use some result that any tensor, let's say epsilon alpha beta, let us say, can be split up into 3 parts. One is the trace of the tensor, which is the sum of the diagonal elements that it contains in whichever basis. Then any other coordinate system that you choose, that sum will be the same because the trace remains invariant. The second is the symmetric part. And the third is the antisymmetric part. Okay? So let me tell you exactly what this is. So epsilon alpha beta, I can write as epsilon gamma gamma delta alpha beta. So this is the pure trace because I summed all of these. Then I can write this as 1/2 of epsilon alpha beta plus epsilon beta alpha minus 1/3 delta gamma gamma, sorry, 2/3 delta gamma gamma of epsilon gamma gamma delta alpha beta. Okay? Then let me write everything down and then I'll show you what it means. Then 1/2 epsilon alpha beta minus epsilon beta alpha. Okay? And let us now see how to understand this. Notice now that all of these terms will now, I think I should have a 1/3 there, I think. Yeah. Just look at this. I've just written a quantity epsilon alpha beta in terms of something on the right hand side. If you look at it carefully, you will notice that's exactly epsilon alpha beta here. The reason is that, let's look at this term. The epsilon beta alpha appears with a minus sign and a factor of half here. This appears with a plus sign and a factor of half here, so that goes away. Okay? This term here, which is this term appears inside the bracket, but this is the same term as here. So the factor of 2 here gets rid of this factor of 2. But otherwise, the 1/3 epsilon gamma gamma delta alpha beta is the same as this term here, but appears with a minus sign. So that goes away. So the only term that survives is 1/2 epsilon alpha beta and 1/2 epsilon alpha beta, which gives me epsilon alpha beta on the left hand side. Okay. So this just looks as though I've written it in a complicated way, but this is sort of showing you that this tensor can be divided into these three parts: the pure trace part, the symmetric traceless part, and the antisymmetric part. Okay. Let me just, this is the pure trace, this is the symmetric and traceless, and this is the antisymmetric part. The great simplification that comes when you consider only isotropic materials is that nothing depends upon this. I can forget about that altogether. So if I want to write the energy as a function of epsilon, I can write this is one contribution to the energy, this is one contribution to the energy, but this I can. In fact, all materials I can do this. The reason is that if I had any contribution from here, that would also, even if I just took it and rotated it rigidly, which I am not actually pulling any part of the system relative to any other part, that should cost zero energy. As we said, when I took the system here and moved it here, it cost me zero energy because I was not pulling any part relative to anything. Similarly, I can take this here and just rotate it. Imagine I'm standing in the center and moving it like that. Every internal part is still at the same relationship with every other internal part. So there is no energy concerned with that. So if you work it out, this is the term that contributes precisely for such a rotation. These other two terms don't contribute. Okay? So finally the answer is that I can write the real relationship between stress and strain for the case of isotropic materials, with whose properties are the same in all directions, is just a factor of K epsilon gamma gamma delta alpha beta plus second term is G epsilon alpha beta plus epsilon beta alpha minus 2 divided by 3 delta alpha beta epsilon gamma gamma. So this whole complicated thing here with lots of indices here, for the case where the system is isotropic, it looks the same in all directions. So it's not a crystal. So for a crystal, I have to worry about more complicated, looking at what are the symmetries of the crystal, how many there are, etc., etc. But for a system that looks exactly the same in any direction I choose to look at, even that simplification happens. So finally, it only depends upon the symmetry, the trace and the symmetric traceless part. And the two elastic constants are quantities called K and G. Okay? So let's just work this out for one particular example, and then maybe we'll stop. We were looking at the case of a system where we took it, the system could sort of go on like that, let's say, and we deformed it like this. Okay? So there are two components. First of all, the x component of the displacement, which is ux, was just gamma times y. Agreed? Uy was uz, which was 0. All right? So this is how we said, remember we said this is y, this is x, these are the displacements. So now we want to ask, what is the stress that gives rise to that strain? So the answer is take this, put it back in there, in terms of these displacements. And from here, if you remember that epsilon, all of these epsilons are just derivatives of the displacement with respect to the r. There's only one derivative that comes, and that is the derivative of the x component with respect to the y component. So that means that sigma x y is g times gamma. This term won't come because there is no volume discharge. only this particular term comes. So put this back, take the epsilon alpha, it's only one of these terms comes in. That is the term that gives you the gamma, because the gamma came from here. So now I have stress on the left hand side is G times the strain, which is the same result that we had earlier. You try that. So we can just work it out. So let us say epsilon alpha beta is the derivative of the alpha component with respect to the beta distance. Okay? Only one component is non-vanishing. Every other component goes to 0. So only component is ux. So that is delta of ux by delta. So I must put for alpha epsilon x something by delta r something, because that's the only one that doesn't vanish. Clear? So this little block here can be either x, it can be y, or it can be z. Okay? If it's x here, that delta ux by delta r x, but that is of course 0, because this depends only upon y, it doesn't depend upon x. So I can put a y here and a y here, that is epsilon xy is delta ux by delta r y. But that works, because that pulls out me a factor of gamma here. So the only, and for z again I get 0. So it's epsilon x y is gamma. Now because I know that sigma xy is now gamma times epsilon xy, I can now go back and figure out what is this relationship here. And this will turn out that G. So this is the only term that comes. Epsilon gamma is 0, because epsilon xx equal to epsilon yy equal to epsilon zz, all of them are 0. The only one that is non-zero is epsilon xy. I can take this and now put it back here. Epsilon xy doesn't figure here. Epsilon xy figures here. And this is 0 and this is 0, because yx is 0. So the answer is that sigma is G times sigma xy is G times gamma. So sigma xy, remember, is the x component to the force directed on a plane that points in the y direction. So it's a shear force. So this is the shear stress gives rise to a strain gamma, and the connection between them is this quantity G. Okay, so this is the simplest example that we considered. We can consider a more complicated example, which maybe I won't do, but that is to take something like this and then exert a force here to elongate it. So what would happen is that this gets pulled out like this, so it becomes longer in this direction and shorter in this direction. So I can have an epsilon x, an epsilon y, and an epsilon z. Sorry, ux, uy, and a uz, from which I can get epsilon xy, epsilon xx, etc., etc., etc. And from here, I can actually compute what is the Young's modulus. The Young's modulus was the force. Remember that if I put a force per unit area acting in this direction and this direction, and the energy and the change in length was delta L by L, the relationship between the force per area sigma and delta L by L was this quantity called the Young's modulus y. Okay, so we can put all of that in back here and basically find that find relationship with the Young's modulus in terms of these other quantities that we've actually written down, which I will probably not do. But again, you see the logic. You prescribe a certain deformation, which you define in terms of the ux's, the ux, uy, and uz. From there, for an isotropic material, I know the connection between the sigma, which is the force per unit area. I know, it's a force at every point. The sigma is telling me about that. This is related to the epsilon, which are derivatives of this, through a matrix. And in this particular case, I've even simplified that to just this particular form. There are only two numbers to tell you. So given any deformation, you can tell me what is the stress tensor that is required to create that deformation. Okay? Yes.
I have some basic questions.
Ask them.
What does this antisymmetric part sigma
So first of all, you'll agree that I can always write this. I've not done anything wrong about it. This is just a mathematical result. Everything else cancels out except this.
Yeah.
But the advantage is that a tensor is like a vector. It transforms in a particular way when you change coordinates. So the pure trace, the symmetric traceless part and the antisymmetric part all transform differently. The pure trace transforms like a scalar, which means it's the same in any coordinate system. This quantity transforms like a vector, which is the same in any coordinate system. And this quantity transforms also like a vector, but with a sort of funny vector here. Well, actually, this transforms like a tensor in any coordinate system, and this transforms like an antisymmetric vector. Okay? Because they're different, you can say that the energetics that I must assign to deformations that are this type, and this type are different. So in principle, I would have said the energy depends on some part of this deformation plus another constant times some part of this deformation plus third constant times some part of this deformation. It would be the most general way of writing it. But now I am saying that it cannot depend upon this part of the deformation. And the argument for that is, if I took it and just rotated it bodily, without changing any of the distances between the atoms themselves, that would give me a non-zero value for this, but a 0 value for this and a 0 value for this. Which would mean that I have an energy cost. I need to impose a certain stress in order just to rotate it. But that shouldn't happen because I'm not changing any of the distances between the particles. So the stress tensor cannot depend upon this part, although it can depend upon this part and this part. That's all that's being said really. Now the condition, the fact that I said that these are much more complicated elastic constants, in order to use this argument I have to say that this tensor transforms under any arbitrary rotation in a particular, it breaks up into three parts that transform differently. But if I look at a crystal, I can't do any arbitrary rotation. There are only certain rotations that are allowed by the symmetry of the crystal. That's why I have many more numbers here. And this simple breaking down just to these parts don't completely describe. So I need more constants that describe more and more different types of deformation that I can do. But in the simplest case, where the material is the same in any direction that I choose, I have only two numbers to worry about, the number that sits in front of this and the number that sits in front of this. And that is the K and the G.
So that is isotropic.
So this is valid only for isotropic solids. Okay. So if I tell you, I will give you an isotropic solid, I say here are the elastic constants K and G. I say pull on the x direction by something, pull on the y direction by something, the z direction by something, creating certain displacements. From that displacement, you can tell me what are the forces I should be applying just by using this formula. That's really the idea. Either I tell you what are the forces that I apply and you calculate for me the displacements, or I tell you what the displacements are and you calculate for me the forces. Because this is just so there are many approximations. First of all, the approximation that the relationship between stress and strain is linear. So you're not allowed to pull it too much because then there becomes a non-linear relationship between stress and strain. And the other is the approximation that this is an isotropic material, which means the relationship between stress and strain only involves two constants, K and G. These can be related very simply to one quantity that you've already calculated, which is a G. But you can also calculate, for example, the bulk modulus will depend only upon this because the only part that changes the volume. Okay? So just think about this as a sort of practical way of calculating things. It looks complicated because there are lots of indices. There are 81 numbers to do here, but it's not that complicated. These are just geometrical relationships between different things that are calculated. Once you understand what these terms mean, you should be able to calculate it for anything. So maybe I will give you some homework in which you.
The network that you described in the
Yeah.
beginning, so that it's, do we consider the network like a cube or like?
So the earlier networks that I showed you, they're best idealized as two-dimensional networks because they tend to be very thin and very long. So even if they sort of have some small thickness, what is usually done is to average over that thickness and represent it only as a two-dimensional material. Then you only don't have to worry about Z, it's just X and Y. There are just displacements in the X and Y direction if you take it to be flat.
So tensors will not come in, or will you have?
They will, but they'll be fewer. They'll just be, all of these tensors will have fewer components. Because the alpha, beta, and so on will only depend upon xy, xy. So if I was to put it back in here, each of these alpha, beta, mu, nu, instead of being 3, can take values only 2 values. So 2 into 2 into 2 into 2 is the number of components of the C in the most general sense. But this remains the same. The K and the G remain the same between 3 dimensions and 2 dimensions. There are still 2 constants to be specified. One is the force that you must apply to compress things, and the other is the force that you must apply to shear things, which you found out here.
So this is the general relation, right? And this we can write down for any solid, like the trace, symmetric, and symmetric.
You can always write epsilon alpha beta like this. That is certainly true because it's just an identity. On the other hand, that doesn't capture the complexity of this particular relationship for a general solid, because a general solid has, this is true, this relationship which says that the strain sigma alpha beta only depends upon this and this is only true for the isotropic case.
Why is antisymmetry vanishing?
Again, for the same reason that that will always vanish, because that says if I make a uniform rotation of everything,
Yeah,
that
that's
term
not true for any solid.
is true for, that is true for any solid.
Yeah, so if
That's true for all
any
solids.
solid, then
Yeah.
whatever solid is there, I can always bring it down to the trace and symmetric part.
But in general, it could depend upon more complicated combinations of these. This term will vanish, that I agree. But in general, I could have, this is the most general relationship that I can write down. That is some simplification of this over here that is valid only for a certain set of materials. Just imposing this condition isn't sufficient to reduce this huge complicated 81 element matrix to something as simple as just 2 components there. In general, there are more things that it multiplies here, even though I've got rid of one part. If in a slightly different way of saying it is that this, I could have G1, G2 depending upon which are the alpha and beta that come here. That won't change anything. It could still, because I'm still allowed to do that by that tensor. And maybe we can show you an example, but probably next time I'll switch to liquids, because that's another important thing that we have to do. And how do these ideas generalize to liquids? And how is it that instead of the strain, we have to worry about the strain rate? How do we describe that? How do we write the equation of motion, which is the Navier-Stokes equation? And then from there, what do we do with it?